just talking about the left and right limits because that's all you've got in your domain. Okay, I meant to write B there. B comes in from the left. And then the other points, call it, so A less than, I'll call it T less than B. Then the limit as X approaches T, not one-sided, is F of T, yeah. So you make a special definition for A and B because you can only come close to them from the left or the right in that definition. Okay, let's do an example. Let's show that the function f of x equal to 1 minus the square root of 1 minus x squared is continuous on the interval, closed interval, -1 to +1. Okay, first question, what is the domain of that function? Can anybody tell me? What do you have to worry about as far as the function being defined?
A negative number.
Right, because you've got that square root, 1 minus x squared must be non-negative. So that the square root of 1 minus x squared is defined. Okay, so that's what you have to worry about. When is 1 minus x squared greater than or equal to 0? Only those x's are going to be in the domain. Well, that would say, let's see, let's work out the inequalities. If I have 1 minus x squared is greater than or equal to 0, then 1 must be greater than or equal to x squared. If I add x squared to both sides of the inequality, that doesn't change the direction of the inequality. But then what does that say? When is x squared less than or equal to 1?
Numbers 20.
Okay, let me change the question a little bit. When is x squared equal to 1?
It will be equal to 1 when x is 1.
Okay, that's one possibility. There's
A
another.
negative one.
Yeah. X is 1 or -1. Okay, let me so that is. Yeah, so whenever you put in 1 and or -1, actually you get the square root of 1 minus 1 squared is 0, and it's also 0 the other one. Someone saying something?
That will be negative.
Pardon? Okay, I didn't get that. Yeah, you get 0 for the square root of x squared minus 1 at 1 and -1. So one way you can think about this inequality, you've got where it's equal to 0, and that's no other numbers give you equal to 0. Okay, so then you can just check the other intervals. Well, if I check, say, I'll color this a different color. Say minus 2 over here. Minus 2, 1 minus 2 squared is 1 minus 4 is less than 0. Okay. So this is less than 0, this whole interval, because we got all the places where it can be equal to 0. On the remaining intervals, it's either got to be negative or positive, and it can't change over. Likewise, if I look at 2 over here, I get 1 minus 2 squared is also 1 minus 4 is less than 0. So everything here is less than 0. And that means that if there's any place where it's greater than 0, it's got to be between minus 1 and plus 1. So check, say, 0. 1 minus 0 squared is plus 1 is greater than 0. So it's greater than 0 there. I only want the places where it's greater than 0. So that means nothing here and nothing there. Okay. So, oops. 1 minus x squared is greater than or equal to 0 precisely on the interval minus 1 to plus 1. And that means that little symbol means therefore. Therefore, the domain of this function is minus 1 to plus 1. Okay, yeah. Think about the domain. First, and well, the domain is in fact that interval. Okay. Okay, so we at least have established where it makes sense to check for continuity, because if you have a number that's not in the domain, the function's not continuous there. And I'm not going to go through the details of this, but let me just sort of sketch the graph of this thing. It looks like this. Right. Okay. Looks like that because it's, remember, f of x is 1 minus the square root of 1 minus x squared. Okay, so continuity. Well, let's take it by cases. The endpoints are kind of special because you can only come into 1 and minus 1 from one side, but the points in the interior, you can come in from both sides. So first, I still didn't leave enough room. I don't know how to do it. Okay, for minus 1 less than a less than 1 of the limit as x approaches a of f of x would be equal to the limit as x approaches a of 1 minus the square root of 1 minus x squared would be, okay, 1's just a constant. We're going to use our limit laws. So it's just going to be limit as x approaches a of 1 is just 1. But then I have to worry about the limit as x approaches a of the square root of 1 minus x squared. And okay, using the limit laws, oh gosh, I'm going to send you a handout today. I'll post it on Blackboard. It has a list of the limit laws. They come up throughout calculus, so it's nice to have at your disposal. For the most part, they're sort of intuitive, but one of them says that as long as that square root's defined, I can take it outside the limit. Okay, and we're going to talk about some more about continuity today. Yeah, from the limit laws, you can do this. Take the limit inside. And then now it's just a polynomial. Okay, 1 minus x squared is just a polynomial. So we can use the direct substitution property for that 1 minus x squared and get a limit. For the limit as x approaches a, 1 minus x squared is just 1 minus a squared. And that is equal, oops, no, undo, okay, where's undo? Oh goodness, what did I do? There we are, okay. Okay, so that takes care of everything between -1 and +1, so something like there, okay. And well, for the 1 and the +1, the limit as x approaches -1, we can only come in from the right to -1 of f of x. But basically, it's the same reasoning. I can take, even though it's a limit from the right, I can, okay, well, change it to f of x there, the function, and then here, change it to 1 minus the limit, and then take the limit inside the square root, even though it's only from one side, okay, and that's f of -1, which is 0, and likewise, checking the +1, that you can only come in from the left there, but the same string of reasoning as we used here will apply with the limit from the, from the left. Okay, so we get 0. And since, okay, so this was f of a, this is f of -1. Oh, I already wrote that. I don't need to write it again. And f of +1 is the same thing. Okay, so for the most part, I'm not going to ask you to go through all these details, but just want to show you how you can step by step apply the limit laws and really be on firm ground when you use a direct substitution property, which is really using continuity. Okay, so questions so far? Is anybody else trying to get in? I think I saw one. Let me go back and check. No, I guess not. Okay. Any questions before I go on? Okay, let's go back. Whoops. Wait a minute. Okay, what happened? All right. Okay. Now share contact. Okay. Have to wait till it starts. All right, there we go. Okay, so some general rules. And basically we talked about this before, only we talked about it in the context of limits and limit laws. That's now going to carry over to continuity, okay, and the direct substitution property. These properties are easy to prove. I'm not going to go over them, the proofs, because it requires the epsilon delta property. And using that real definition of limit, And just not sure I want to get into that right now. So, but okay, theorem. If f and g are continuous at the number a, and c is a constant, then the following functions are also continuous at a. And let's see if maybe I can. Okay, so f plus g, if you add two continuous functions, you get a continuous function. Of course, if you're talking about just one number, it's got to be the same number. The difference, okay, the difference also is continuous. A constant times a function is continuous. Product of two functions is continuous. The quotient of the two functions is continuous. And of course, for quotients, you have to worry about the denominator being 0. As long as g of a is not 0, f over g is also continuous. And then facts, okay. We talked about polynomials having limits everywhere. Well, they are continuous everywhere too. And that follows pretty easily from the fact that they have the limits. Any polynomial is continuous everywhere. That is, it's continuous on the whole real line. Any rational function is continuous as long as it is defined. Okay, you have to worry about with a rational function. Okay, let's go back a little bit here. Remember, a polynomial, something like x cubed plus 2x is f. Okay, that means something like that type of function. Rational functions, yeah, and in particular, the powers on x have to be non-negative integer powers. And then you multiply those by constants and add them all up. That's how you get a polynomial. A rational function has the form polynomial over polynomial. So of course you got to worry about when q of x is defined. And okay, here's a whole another list of continuous functions. Well, we talked about polynomials and rational functions already, but okay, someone was asking, Mr. Levy was asking about root functions. There they are. Root functions are continuous where they are defined. Okay, so square roots are only defined when the number under the square root's non-negative, and fourth roots likewise. But cube roots are defined everywhere. So it all depends on the domain. For any root function, as long as a is in the domain of that root function, then that root function is continuous at a. Trigonometric functions, likewise, as long as they are defined at a number a, they are continuous at that number a. And then exponential and log functions, I'm not going to talk about these very much until later in the semester, but they are certainly important classes of functions. Especially, okay, you hear this word exponential thrown around all the time about this pandemic. Okay, we're going to learn what it really means. Exponential growth, really different from polynomial growth or linear growth or any other kind of thing. We're going to see how. Okay, let's compute a limit using, okay, these facts. So, okay, we want to find this limit. Now, okay, this is a rational function, right? It's a polynomial, third degree polynomial divided by a first degree polynomial. So, oh, I'm forgetting to record. Geez, okay, let me go back. No, all right. Let me go back and turn the recording on. Helps a lot if I. Please remind me to do that so that you will have these. Mr. Flores is also recording, okay? But Okay. And let's see if anybody else wants to be admitted. No. All right. You guys remind me to record. I'd like for you to have as much of a record of everything as possible. Nope, nope, you can't do that. Okay. Do this. Okay. Okay, so we want to find this limit and, well, show that it's continuous here. For one thing, where is, I didn't finish writing that. It's a rational function. Well, okay, you have to worry about where the denominator is equal to 0, because that's not in the domain. You'd be trying to divide by 0. Well, that would say 5 is equal to 3x, 5/3 is equal to x. So it's equal to, oops, 0 at 5/3, and that means that 5/3 is not in the domain of f. Okay, 5/3 is not in the domain, but that's the only number that's not in the domain. That's the only number where 5 minus 3x is equal to 0. Minus 2 is fine. So this function, f is continuous. It's a rational function. Defined at a equal to minus 2. So it is continuous there. And that means we can just plug in. And of course, I didn't leave enough room. So the limit as x approaches minus 2 of x cubed plus 2x minus 1 over 5 minus 3x. And let's make sure I got the right function. No, that's supposed to be 2x. No. Okay, that's supposed to be 2x squared. Yeah, okay. It's just equal to f of minus 2, which is minus 8. Let's see, so 4 times 2 is 8, minus 1 over 5 plus 6. It's because that's a minus 2. And that's equal to minus 1 over 11. Yeah, so it's equal to let's minus 1 over 11, because you can just plug in there. Okay, let's see. It's 8:30. I don't want to go on too long today because I know some people are still having problems with everything. Okay, but just a little more. If f is continuous at the number b and the limit as x approaches a of g of x is b, then the limit as x approaches a of f of g of x is f of b. In other words, the limit as x approaches a of f of g of x is equal to, okay, f of the limit as x approaches a of g of x. So you can take that limit thing and sort of move it inside f. Okay. That's continuity. And this is talking about dealing with what you call composite functions. When we moved the limit inside the square root, we were doing the same thing. We took, oh gosh, I forget. It was the limit as, oh, it doesn't really matter. Okay. We took a between -1 and +1, and we were worried about the limit as x approaches a, this is a piece of that function, of 1 minus x squared. And we just took the limit inside the square root, right? We're doing, this is actually an application of that theorem. Oops, no. Is equal to the square root of the limit. Oops, no, okay. That should be x, oops, okay, well, let's just start over there. That kind of got messed up. The limit as x approaches a of 1 minus x squared, okay. So you can take, here the function is the square root of x. F of x would be the square root of x. But this theorem allows you to take the limit from outside the square root to inside the square root. And also a corollary to this theorem, if G is continuous at A and F is continuous at G of A, then the function f of G, which sometimes you'll write with a little circle to indicate composition. Yeah, this means the same thing as this. It's also continuous at A. Okay, so that strengthens, or at least doesn't really strengthen. It's assuming a little bit more about G. And that means compositions of functions are continuous too. Okay, what else do I want to talk about today? Okay, well, let's do a couple of examples, and then I think I'm just gonna stop. Actually, we do have some catching up to do, but it really helps that we're meeting 5 days a week. I don't think it's going to be a problem at all. Okay, let's look at a couple of examples. Okay, and the question is, where are the functions continuous? That is for what numbers? sorry. Why does it do that? All right. Here's the first one. F of x is equal to the sine of x squared. Now, this is a composite function. Oh. Okay, so the g of x here would be x squared. So this is a composite. We have f of g of x. No, that's not right. Never mind. Okay. I'll have to tell what the outside is too. So, and I'll let h of x equal to the sine of x. Okay. F is a composite function. F is equal to h of g of x. Now, this is not a product of these two functions. It's not a product. It's a composite because I'm putting g inside h. Okay. So it's, I'm sorry, my skills deteriorated over the 4-day period. So g of x is x squared. Okay, I replace that for g of x. And then h is the sine of x, so that means I put x squared in the place of x. And there you have it. Okay. So sine of x squared, well, so we want to know where g is continuous and where h is continuous. That would help. Where is g of x equal to x squared continuous? Can anybody tell me?
Wouldn't it be all real numbers?
Yes, it would be. It's for all real numbers. Thank you, Mr. Levy. I recognize your voice. Okay. For all the reals. Because it's a polynomial, right? It's a polynomial. It's defined everywhere. It's continuous everywhere. Okay. So it's for all the reals for G. And second question, where is H continuous? Anybody? Maybe not Mr. Levy this time. Come on, somebody get brave. Nobody. Well, what's the domain of the sine function?
It's -1 and 1.
No, the sine function, okay, the arc sine is defined on -1 to 1. That's the inverse of the sine. Okay, the sine function is actually defined for all real numbers, right? But thank you very much for answering. Okay, I appreciate it. Yeah. For the sine function, and when you graph it, looks like this. Okay, this is not a good picture, but this, the oscillations are supposed to be very even. So okay, not a great picture, but that's what basically what it does. The domain of the sine is all the reals. And we just had a little, well, it was a theorem, really. I think I stated it as a fact. So we, in the first example, we used this theorem about composites. But now, okay, the following types of functions are continuous on their domains. It includes the trig functions. Well, the sine is a trig function. The sine is defined everywhere. That is for each real number. Therefore, the sine is continuous everywhere. So sine of x equal to h of x is continuous everywhere. And if they're both continuous everywhere, so is their composition. Then h of g of x, which is equal to f of x, is continuous everywhere. And okay, now we take this function and we take this function and we compose them to form the function f, but from the little theorems we just had, that function's continuous everywhere. Okay, one more example. Let's see. Okay, we're going to talk about the inverse. I didn't mention those. Okay, let me not get into that. How about this? The tangent of x minus the square root of x. Okay, so that's the difference of two functions. And we want to know where this function is continuous. Well, as long as, let's see, this is a difference of two functions, so we have to worry about where each of the functions is continuous. So let's break it up. Let g of x equal the tangent of x, and h of x equal to square root of x. The tangent of x, okay, let me graph it for you. And I hope that you have pictures of these trig functions in your mind. They're important functions. Tangent of x, remember, got these vertical asymptotes. Anytime you have a vertical asymptote, function is not continuous there. And let's see, where are, that's at pi over 2, that's at minus pi over 2, that's at 3 pi over 2, and so forth. At odd multiples of pi over 2, you have these asymptotes. Okay, so we said that the trig functions were continuous as long as they were defined, continuous on their domains. This one, g, is continuous. Oh. I'm going to write it out this way. It's at a bunch of open intervals. Okay, minus pi over 2 to pi over 2, that's that interval right there. But then, okay, define it at pi over 2, but it's nice and continuous from pi over 2 to 3 pi over 2, and you just keep going. And you can keep going in the other direction too. Minus 3 pi over 2 to minus pi over 2. Okay, so it's continuous on an infinite collection of open intervals, disjoint open intervals, as not continuous at any of the endpoints of those open intervals. Okay, so we have continuity information about the tangent. H of x is the square root of x. Well, let's graph that. That looks something like that. The domain is x greater than or equal to 0. This is a root function. So it's continuous on its domain. And that would be 0 to infinity. Okay, notice I put an open to parent at infinity because infinity is not a number and I cannot include it in an interval. Okay, so for this function, f is equal to g of x minus h of x, which is equal to the tangent of x minus the square root of x. F is continuous on the intersection of those two domains, okay? For f to be defined, g must be defined and h must be defined. So that means that basically I look at the intersection of the domains. I have to throw out all negative numbers because of the square root function. I have to throw out all odd multiples of pi over 2 because of the tangent function. But let's see, so all these intervals, okay, this one's going to be halved because from minus pi over 2 up to 0 get negative numbers, but okay, putting all that together, f is continuous on, okay, 0 to pi over 2. Only got half of that interval because the other half has negative numbers in it. But then the rest continues as before, pi over 2 to 3 pi over 2, 3 pi over 2 to 5 pi over 2, and so forth. And that just goes on forever. Okay. Okay. I think I will stop there. Are there any questions? Nobody? Okay. Okay. Let me go back to and share screen. Yeah, homework. Your homework's not due until Friday. It's not reasonable for me to expect people to have gotten their homework in this past Friday after that storm. Okay, just not reasonable. My life was kind of messed up for 4 days, although I must say it's the first time I've been out of the house in 5 months. and I had a lot of fun with my friends. But yeah, the homework that was marked for August 28th is now due on September 4th. I'm going to make your next week's homework a little bit longer to compensate for the missed days and the missed week. But let's just do it that way. I have not made up the next homework assignment yet. Okay. Any questions?
I had one real quick.
Okay.
If we did the homework for last week and we already sent that off, is there anything else you want us to do this week, or just study what we're
Well,
going over?
actually, Mr. Miller wrote me a note about you, and he said you only submitted one problem.
Did it? Okay, I'll check the PDF because. Okay.
Yeah, if you've already submitted something and maybe it wasn't complete or whatever, look, if you can't do the entire homework assignment, I want you to submit what you have done on time. Okay, that's the rule. You'll get some credit for it. But since it's not due until Friday, you can do it over and resubmit something, and we'll grade that.
Okay, thank you.
Okay. Okay. Anything else? Okay, JPEG, no, I want a PDF, please. I want a PDF because if I don't get it as a PDF, I have a very hard time grading it on the computer. And all right, in order to do that myself, I upgraded my Adobe Acrobat. And it costs $14 a month or something. But there are free options out there. And in fact, there's an app that a free app that you can put on your cell phone that will turn picture files into PDF files. Okay. Also, so that's one option. If you take pictures of your homework, if you work your homework out on paper and then scan it into a computer, you can save it as a PDF file. So that's another easy way to do it. Yeah. So somehow get it in the form of one PDF file.
Or
Pardon?
if you have your iOS device, you can go onto the Notes app, and they already have a option where you can scan it in as well.
Okay. I've learned a lot of technology, but I still don't know all the ins and outs of that. So maybe you guys can ask Mr. Levy how to do that, and he can fill you in. Okay. Any other questions? Yeah, you can submit it as a chat if you want. The only thing about chat is when I'm on the shared screen, I don't see them popping up. But okay, let me check them. Okay, let's see. Okay, well, you all are answering your own questions, so that's good. Okay. Okay, so we will call it a day, and I hope more people will be back tomorrow. I think tomorrow we're going to start talking about a very special limit called the derivative. Okay, very useful limit.
Okay, I'm gonna head out. Bye everybody, and hope everyone's internet gets better.
Yeah.
All right. Have a great day, everybody.
Yeah. Bye.
You too,
Stick
Bridget.
around if you want to ask a question. But go ahead and leave now. Class is over.